Hello, my name is Hadziioannou, and we're going to find out whether it's possible to do ambient noise interferometry with rotational ground motion. I'll present work that I did with a student, Paul Neumann, at the University of Hamburg. And the work is done in context of the European Union-funded ROMI project, which involves the PI, Heiner Igel and Joachim Wassermann, and relies heavily on the expertise of Ulrich Schreiber. And finally, a lot of people from all around the world made the ROMI project possible. Way too many to list here. So in this session, we're seeing that new sensing technologies are currently emerging in seismology, and those can measure ground motion beyond the conventional seismic translation measurements. In this presentation, I'll focus on rotational ground motion measurements. And so far, studies of rotational motion are based on recordings of earthquakes or active sources, so quite strong ground motion. Here, we're going to push the limit toward the very weak motion associated with ocean-generated ambient seismic noise. Our aim is to show the potential of using these measurements in the context of ambient noise interferometry, but first, we need to establish that we can detect such weak motions in the first place. And I will show you that we can now detect both the secondary and the weaker primary microseism with ring lasers. Next, we need to verify that the ambient noise interferometry works with rotational motion, and this has been shown in theory by Patrick Patz and co-authors, but so far it has not been done with real rotational data yet. Throughout this talk, I'm going to be using recordings from two ring lasers in Germany, the G-ring at the Wetzel Observatory and ROMI at the Fürstenfeldbruck Observatory near Munich, at a distance of approximately 160 kilometers. This last one is the first ring laser to record three components of rotational motion. These are the most sensitive instruments at the moment that offer a local direct measurement of rotational ground motion. What's important to note here is that at each of those two locations, there's a broadband seismometer co-located with a ring laser, and these will also be used in our analysis. Further note is that we're going to be focusing on the vertical component of rotation, which corresponds to rotations in the horizontal plane and is therefore associated with SH-type motions and with love waves. So let's focus first on the ring laser in Wetzel, since it has been running the longest, and we want to see whether it can pick up ocean-generated seismic noise. First, I'm going to show you what the broadband seismometer at this observatory picks up. So here you see a PPSD plot showing the frequency content of 1 month of seismic noise recorded by the seismometer. We can clearly see a peak here between 0.1 and 0.2 hertz approximately for the secondary microseism, and you can make out a much smaller peak here at lower frequencies for the primary microseism. So this is only background noise, no earthquakes, and what you see here is the imprint of ocean-generated seismic noise. Now, if we look at the ring laser at the same observatory, so measuring rotations, you can clearly see the peak of the secondary microseism as well. And up until recently, the instrument sensitivity was such that we could not detect any seismic waves below this level. But in about mid-2017, they improved the instrument and thereby lowering the sensitivity limit to about this level. And now, just about here, just above the sensitivity limit, you can see the primary microseism peaking out. So that looks good, but are we really sure that this is the primary microseism and not just some other bump in the spectrum? So in order to make sure of that, we're going to exploit the coherence of the wave field and exploit a useful property of rotations, namely that there is a simple relation between rotation and translation. Here we have the transverse acceleration with a certain expression for its waveform, and the rotation rate around the vertical axis that is given by this expression for the waveform. And you'll see that these two waveforms are very similar, except for a factor of 2 times the apparent phase velocity. What this tells us is that if you have the recording of the transverse acceleration, so what a classic seismometer measures, at the same location as a recording of the rotation rate, you can do 2 things. You can determine the apparent phase velocity with a single point measurement, which is very interesting, but we're not going to be using it here. And you can find the direction towards the source by exploiting the similarity of the waveforms. Okay, so we wanted to figure out if this bump is really the primary microseism, and we're going to do that by looking if the associated noise is really coming from a specific source direction. So we're going to exploit that property that the rotation rate and acceleration should be in phase. And here you see a plot that we're going to fill in with a certain time length and with a range of back azimuth. And we're going to pick a time window and just try out all the different back azimuths. So what we did is simply take a short time window of transverse acceleration and orient that towards a certain back azimuth, let's say minus 60 here. Then you compare the resulting waveform to the rotation rate waveform that was measured at the same location. And if the two waveforms, transverse and rotation rate, are the same, that means that you're pointing in the correct direction where the wave actually came from. If they're not the same, that means you're pointing in the wrong direction. So the similarity of the waveforms is expressed here in this color scale that represents the correlation coefficient. And this is what the result looks like for a time window in January 2018. And you can see that there's clearly a high coherence between seismometer recording and the ring laser recording, specifically for back azimuths around 0. This would be pointing approximately north, and indeed that fits very well with observations that we have from classic beamforming. So in a previous study, we found that a source of love waves in the primary microseism towards the north corresponds to a source region north of Norway that is especially active in winter. Okay, so that fits quite nicely, and we can conclude that we are picking up the primary microseism here. And we can conclude that the ring laser in Wetzel is now sufficiently sensitive enough to pick up the primary microseism as well as the secondary microseism. This is interesting because it shows us that very faint signals can now be detected, and it opens the way towards more ambient noise analysis with rotational motions, such as, for example, the possibility of doing ambient noise interferometry with rotation signals. That's the second topic I want to address here. But first, a very quick introduction of what seismic noise interferometry actually is. So the main thing to remember is that if you have 2 seismic stations that are surrounded by seismic noise sources, we can take the noise recorded at each of those stations and cross-correlate it. And the shape of this correlation function will correspond to the Green's function between the 2 stations. What that means is that one side of the signal will look as if there was an impulse source at your station A that was recorded at station B, and the other side of your signal will look like there was an impulse source at your station B recorded at your station A. So in a way, using only ambient noise sources, we can extract useful seismograms, essentially turning our seismometers into virtual sources. So this method has been embraced by the seismological community over the past decade, which is evidenced by hundreds, if not thousands, of publications. But so far, it has only been applied to seismometers or translational motions, and not yet with rotation motion. So in order to test whether that works, we're going to need ambient noise on 2 sensors. So let's have a look at what we have on our 2 ring lasers here. We know that we can measure the primary and secondary ocean microseism on the ring laser in Wetzel, but the primary microseism is very weak and it's not yet detected by the other ring laser. So we're going to focus on the secondary microseism. And here we see what the secondary microseism looks like from the point of view of the ring laser in Wetzel here. And you can see that there is a coherent noise source about 60 degrees westward. If we compare that to the signal detected at the other ring laser at Romy here, we can see that it sees secondary microseism coming from the northwest as well. Again, we know from previous beamforming studies that this points towards the North Atlantic, which is a known source region for the secondary microseism. Okay, so that means that we have seismic noise to work with at both of our ring lasers, and we can proceed with noise interferometry. So we've taken a year of ambient noise, filtered it between 5 and 10 second periods to isolate the secondary microseism, and I'll show you what the noise correlation signals look like. Again, I'll show you first what it looks like for the classical seismometers. So this is the noise correlation between the two seismometers that are installed at these observatories respectively. It's symmetric, approximately around 0, with the signal in this direction corresponding to a wave propagating from Romy to Erlaz, and the signal in that direction corresponding to a seismic wave propagating the other way. The two stations are about 160 kilometers apart, and here I've indicated the expected arrival times of love waves. And you can see that that fits nicely with the main energy arriving on our signals. Okay, so this is what a noise correlation looks like for seismometer data, but we already know that that works. And the question was whether it works for rotations as well. So let me show you here. The solid red line shows what the noise correlation looks like for a rotation rate. And you'll see that in particular around the love wave arrivals, the waveforms match very nicely. And if you remember from before, that is what we expect. The rotation rate should have the same waveform as the transverse acceleration, although there's a little bit of additional information in amplitude ratios and small waveform differences. We can also compare this to a synthetic signal, here simply for a 1D model for PREM, and again we can see that the phase of the love wave arrivals matches very nicely. So we can conclude that seismic noise interferometry for ground motion works in principle. To summarize, what we've seen is that we can now detect both the secondary and the primary microseism on ring lasers. And we've seen that the first results of rotational noise interferometry between two ring lasers are very promising. In general, we can say that this opens the way for seismic noise analysis with rotational motion, and that unlocks 3 additional components of ground motion, and with that provides access to additional information about the seismic wave field. And finally, in a view towards the future, I would like to use this occasion to point out a project that will start very soon. So in spring next year, a new innovative training network called SPIN will start. And this project is funded by the European Union Horizon 2020 program. And it will focus on integrating the latest ground motion sensing technology, such as rotations, DAS fiber optics, and array-derived quantities from large N arrays, to integrate those into daily observation practice. So we'll work on improving monitoring of geohazards and look at the effects of small-scale heterogeneities on wave propagation. But most importantly, this is a training network, and the goal is to transfer this knowledge to the next generation of scientists. So to achieve that, the network will offer 15 PhD positions across Europe at the consortium listed here. And if you're interested in that, keep an eye on this website here, which will be updated regularly. And finally, if you want to have a look at these slides again or at references, you will be able to find them on my website. Thank you very much.